In the previous lessons, we learned how to use the stoichiometry flowchart to determine the number of liters for the volume of gas from a given moles or a given mass. Now, in order to do that, we have to assume that the condition is at STP, which is standard temperature and pressure. Well, the word standard means the values of temperature must be 0 Celsius, and that standard pressure is 1 atm. But the reality is that most of our experiment will not be at 0 Celsius. That's super cold. Well, that's freezing, okay? And then we don't really have control of the pressure at 1 atm most of the time. So today we are going to look at an equation that allows us to determine the volume of any gas at any temperature and at any pressure. And that equation is PV equal to nRT. Now, the only problem with this equation is this. In order to use it, we have to assume that the gas molecules are behaving ideally. This equation is called Ideal's gas law. Before we look at a specific example, let's look at this sample of gas molecules, which is water, contained in a container. Well, we notice we can measure the temperature of whatever inside this container, as well as the pressure. And notice the gas molecules are colliding against each other as well as against the wall. And that's what's causing the pressure. Now we have looked how gas behave ideally in a container. Let's look at the theory that explains the Ideal's gas law. According to the kinetic molecular theory, gas particles at sufficiently high temperature and low pressure behave ideally. So what are the characteristics of behave ideally? Well, first of all, gas particles are in continuous random motion, and the collision between gas particles or between gases and the walls of the container are perfectly elastic. Now we have a new term, elastic. Basically, when they collide, no energy is lost, okay? So the energy is transferred from one substance to another substance. Then the pressure exerted by a gas is due to the collision of the particles with the wall of the container. And notice how the gas molecules are colliding against the wall, and that causes the pressure of whatever inside this container. And the volume of individual gas particles is negligible, which means unimportant. Then we have the temperature of a gas is a measure of the average kinetic energy of the particles. And of course, the word kinetic energy, or the word kinetic, is motion. So the higher the temperature, the greater the average kinetic energy, which means the particle will move faster at higher temperature. Then lastly, sample gas can be described by 4 variables, which is pressure, temperature, volume, and the number of mole. And that can be given in terms of the Ideal's gas law, PV equal to nRT. So P is your pressure, V is your volume, N is your number of mole. Your R, we will talk about R later, but let's look at T. T is your temperature. Well, what is R? R is the universal gas constant. And the values of the gas constant is 0.0821 liters times atm over mole and over Kelvin. Now, the reasons why is it over because of that negative right there. That negative indicates that mole is on the bottom. So mole and Kelvin are on the bottom, where liter and atm is on top. So keep that in mind. This is the result of the power to the -1. Now, if we look at the gas constant, notice how we have liter, right? So that tells you that the volume must be in liter. And we have atm, that is the unit for pressure. So your pressure must be converted to atm, or atmosphere. And then we have mole, so therefore the number of mole must be in mole. And lastly, we have K. K is your temperature in Kelvin, so your temperature must be in K. So by looking at the unit of the gas constant, we can actually learn about the unit of each of the variable in the Ideal's gas law. Let's do an example problem together. 1.5 moles of dry ice, carbon dioxide, will make how many liters of carbon dioxide at 1 atmospheric pressure and 298 Kelvin? And we are given the molar mass of carbon dioxide as well as the gas constant. Well, again, we are solving problems using the ideal gas law. And we have this PV equal to nRT. What are we looking for? We are looking for how many liter. So what is the unit liter represent? It is volume. So we're looking for V. So if we want to isolate V, we would have to divide both sides by P, isn't it? And P cancel each other out. And now we have V equal to nRT divided by P. Well, all we have to do now is just plug in the values. So first of all, we have the number of mole, which is N right there. Then we also have the temperature right there. Then we also have the pressure right there as well. And the R constant is right here. So let's plug it in. So at 1.5, notice I ignore the unit for now, okay? Because I know the unit for volume is in liter already. And then the R constant is 0.0821. And then the temperature is 298 divided by, and the volume is equal to 36.7 liters of carbon dioxide gas. Let's try a more complicated problem. 7.5 grams of dry ice, which is carbon dioxide, will make how many liters of carbon dioxide at 1 atmospheric pressure and 298 Kelvin? And we are given the molar mass of carbon dioxide as well as the universal constant. So this problem is very similar to the previous problem, except now that that number of gram is not mole. So what do we have to do? Well, first of all, we have to realize that how many moles are in 7.5 grams of carbon dioxide. So we have to take that number, convert to mole, because our unit must be in mole. So 7.5 grams of CO2, and we learned that using the stoichiometry flowchart, from mass to mole is the conversion factor of molar mass. So I'm going to multiply that by the molar mass. And to get from gram to mole, I'm going to multiply by molar mass, which is 1 moles of CO2 equal to 44.01. And that's the molar mass of carbon dioxide right there. And grams of CO2. Now I'm going to rewrite this. 7.5 grams of CO2 time, this is grams, so the grams is going to be on the bottom, 44.01 grams of CO2, so that way it cancels out, and this part will be on top, so 1 mole of CO2. Now let's plug into our calculator. 7.5 times 1 divided by 44.01. And this gives us 0.170 mole of CO2. There you go. So now we have our number of mole, which is N. So let's go back and solve the problem. The same thing, we have PV equal to nRT. Okay, now we're solving for the volume again. The volume is equal to nRT divided by P. We just bring the P down here. That's how it is. So let's plug it in. We have the number of mole, which is equal to 0.170, which is solved from 7.5 grams of carbon dioxide, times the R constant, which is 0.0821, and then the temperature is 298, divided by the pressure, which is 1.0. Then plug in our calculator, 0.170 times 0.0821 times 298 divided by 1. This gives us the volume of 4.16 liter. Now do you see how different unit will change the values of our calculation? So make sure you change all the values in the correct unit given in the gas constant. And let's try another problem where we had to solve for a different variable using the ideal gas law. A sample of carbon dioxide are held in a 2.5 liter container at 600 Kelvin and 5 atm pressure. How many moles of the gas are in the container? So again, we are using the ideal gas law because it's not at standard temperature and pressure. So we have PV equal to nRT again. But in this case, we are solving for N. So to solve for N, we're just going to bring down this over here. We bring over, so this is going to be on the bottom. So we have N, which is equal now to PV divided by RT. So let's plug in our values. Well, first of all, let's look at our pressure. What is our pressure? atm, that's checked, good. Volume is in liter, that's right. And the R constant, we don't care, it's given to us. And the temperature is in Kelvin. Where's the temperature? Right there in Kelvin. Check. So everything is done. Now let's plug it in. So we are in the correct unit. Now let's plug into the formula. In this case, pressure is 5.0 and the volume is 2.5 liter divided by the R constant, which is 0.0821 times the temperature, which is 600 Kelvin. And now we just plug into a calculator. 5 times 2.5 divided by 0.0821 divided by again by 600. This gives us the number of moles equal to 0.254 moles of CO2. Now let's do another problem where we have to solve for the number of moles again. A sample oxygen gas, notice I changed carbon dioxide to oxygen, are held in 3.5 liter container at 398 Kelvin and at 5 atm pressure. How many moles of the gas are in the container? And I give you molar mass of carbon dioxide. Do we care? No, we don't, because we're talking about oxygen. But the R constant for any gas will be the same. So again, we have PV equal to nRT. And again, to solve for the number of mole, okay, which is this one here, we have to divide both sides by RT. So that now they cancel out, simplify to equal to 1. Okay, so we have N equal to PV over RT. Let's plug it in. But before we do that, we have to check that our unit are right. Well, pressure, it has to be in ATM. Is that right? Yes. How about volume? Is it in liter? Yes. How about the R constant? Well, it's just a constant. And then the temperature is in Kelvin. Yes. So now let's plug it in. So we have pressure is equal to 5.0. Your volume is 3.5. Nice. And then the R constant is 0.0821. And your temperature is what? 398. And now, let's plug into a calculator. 5.0 times 3.5 divided by 0.0821 divided again by 398. And this gives us 0.536. And that would be the unit of mole of O2. There you go.